Okay, here we are again. Um, Today we're talking about maps and mapping systems. So, and there are a lot of different ways to use coordinate systems, how to use maps, how to project and gauge certain features of the Earth. In fact, it isn't just limited just to Earth. In fact, for years, Rand McNally used to sell this huge map of the Moon, all the different features of it, and all the different landing spots of the Apollo astronauts. But get down here to the real basics. Cartography. What we're talking about here. It's the art, science, and technique of making maps. Time-honored ancient practice. These maps date back thousands of years, even. So even today, the globes you see and buy at the stores, those are actually handmade. Some are just small, just for desktop use, for use in classrooms. You also have the larger ones. You also have the real fancy ones that open up into a bar. But go back more than 2,000 years, printing the works of astronomer Ptolemy, Greco-Roman mar- uh, maritime needs helped improve cartography. See, one thing about making maps is, in order to be any good, it has to be to scale. You have to be able to show certain features in relative proportion to whatever you've got. And that takes a lot of practice. So as mathematics improved, as measuring techniques improved, especially the ancient Greeks, ancient Romans, map making improved. And there's need for that because, for one thing, you've got a lot of, one thing, scientists are wanting better, more accurate instruments. But also, particularly among the Greeks and the Romans, they had this huge sea trade empire across the Mediterranean to maintain. They need to know how long it takes to get from point A to point B. Because even then, time is money. Well, and as nation states built and developed, shipping interests increased. That prompted increased need for occasional surveys of coastlines. When the Spanish were exploring the New World, they made map making a priority. And they would map carefully the coastlines of North and South America, all the different islands, and they present these maps to the Royal Observatory in Madrid. And you go to that map room they have, they measure these maps not just in the amount of maps and the amount of paper they have, not in feet or meters, but in kilometers. Just miles and miles of nothing but maps. But even then, as painstakingly the process was of making maps, they were still inaccurate. They see these old maps in history books and everything, how out of proportion everything is, and how lack of features beyond the coastline they have because they really didn't know anything about the coastline. They really didn't know much about scale and proportion. But slowly they started improving this. And so by the 17th century, the English and French especially saw the importance of creating national surveys for their own, for measuring their own interior resources, but also overseas sources, plus maps of the seas to in shipping lanes to make sure that they could get goods from point A to point B quickly and safely, or as quickly and safely as it could in the 17th century. Like I said, that increased over time. Maps are used by surveyors to determine property lines, and that means tax rates for communities. They're used by emergency services to see to measure response times to potential emergencies and routes to potential hospitals, major traffic areas. How to get from point A, their base, to point B, point of emergency, to point C, hospital. Military, of course, used for looking at for tactical reasons to gauge, to measure possible battle sites, study past battles, and plan for present and future battles. Um, Maps are a critical part of predicting the weather. So you can pinpoint where a certain weather system is going to impact in a certain area. And it's not just the surface, it's also under the surface too. Mine space is routinely mapped and cataloged, but also submarines. Now, if you ever saw that old movie, The Hunt for Red October, a lot of what they did, that underwater navigation, was by careful, painstaking maps. Exact detail. Yeah. Exact depth, what a canyon or reef you're at, elevation, so you know where you need to go and not run into anything. Especially if you can't use sonar to let anybody know where you're at. Spanish and the Portuguese voyages of discovery in the 1500s and 1600s to detailed maps used for later study. And over time, these maps gradually got more and more accurate. Now, one feature among a lot of maps, of course, is the north and south geographic poles. North Pole, of course, being at 90 degrees north latitude, the south being at 90 degrees south latitude. The northernmost and southernmost points you can get anywhere on the Earth. The same with any other planet. Because they're all round, they all have north and south poles. But there's more than one kind of pole. You also have the magnetic poles. Because the Earth has a molten core made out of iron. And iron, when it spins, a lot of electrons means creates a magnetic field. The Earth is basically a giant magnet. And one thing about magnets is they all have their own north and south pole. So northward goes out, comes in, so forth. The thing about these poles is, of course, the poles of the same type will repel each other, but the poles of the opposite type will attract. North and south attracts, but north and north repel. The thing is, though, that's not exactly at 90 degrees north latitude. It's just slightly off. The Earth is tilted at an angle of about 23 degrees. But the north and south magnetic poles are some ways south of the magnetic pole. And of course, magnetic field lines, they extend out into space. They are shaped by the sun's solar winds. But basically, as the Earth rotates, you've got this huge magnet. That's what makes magnets work. Because you're holding a compass, they are attracted by the magnetic field lines of the Earth. And always points towards magnetic north. Now, magnetic north is in northern Canada. But because it is a world in motion, because our core, because of various natural forces, the magnetic field shifts a little bit, wobbles a little bit. Nothing much, but kind of. But every few thousand years or so, the poles actually flip. Why exactly, we're not sure. Actually, does it cause any kind of major problems in the Earth? No. Just means your compass is going to start working the opposite way, but not a big deal. We can tell that because as certain kinds of rock are formed and cool, they are formed, uh, their magnetic features are oriented towards the magnetic North Pole. They notice every few thousand years, these orientation lines shift back and forth, back and forth. Now, a circle, of course, is 360 degrees. Distance between two poles, of course, is 180 degrees. Distance between the equator and each pole is 90 degrees. Polar circumference that is 24,899 miles. Earth from pole to pole, back again. So each degree of latitude is actually about 69 miles, or 111 kilometers. As we can see here, they're all evenly spaced out, going from north to south, but east to west, they get closer to closer each other as they get closer to the poles, intersecting at the poles. So you can't have quite that same measurement. Of course, the polar circumference is slightly different from the equatorial circumference. Why? Because the Earth has been spinning for so many billions of years. It actually has a little bit of a bulge in the middle. It's a centrifugal force. All the planets have that. Now, of course, these degrees are divided into minutes and seconds, 60 minutes and 60 per degree and 60 seconds per minute. I'll give you an example here of downtown Chicago. Their coordinates are at 41 degrees, 51 minutes, 50 seconds north latitude. You have coordinates for El Dorado, Arkansas, downtown. 33 degrees, 12 minutes, 49 seconds north latitude. 92 degrees, 39 minutes, 45 seconds west longitude. Basically 33 north, 92 west. At an elevation of 272 feet above sea level. Now, of course, like I said, they had to have a starting line for all this. The prime meridian runs through the Royal Observatory of Greenwich, England. And it's decided by an international convention in 1884. Now, of course, the Earth is rotating 360 degrees, and it rotates 360 degrees in 23 hours and 56 minutes. Not quite a 24-hour day. Except to be more precise, 23 hours, 56 minutes, maybe about 4 or 5 seconds. And it actually shifts a little bit from one year to another. So one year, regular year, actually what might be a second or two longer than the previous year. And it orbits the sun not in 365 days, but about 365 and a quarter days. Which is why, like this year, 2024, we have a leap day. 29th day of February, once every 4 years, so everything gets back in alignment again. So time is really dependent on longitude because we measure so much of time based on the position of the sun in the sky. For example, 12 a.m. or 12 p.m. These being Latin terms, ante-meridian. 12 hours before the meridian, 12 hours post-meridian. Because you're moving from the high point of the sun of the day. Because we're just not kind of people who are going to accept that 12 noon is middle of the night. Even though when it's midnight here, it's 12 noon somewhere opposite side of the world. So when we got New Year's, like I say, it's midnight in Australia and they're celebrating New Year's Day, but it's still middle of the day on New Year's Eve for us. It's all based on time. And so to make that a little bit more even, we divided the world by international convention into 24 time zones. Because right now it's 11:30 in Hawaii, here in El Dorado, but it's 4:30 a.m. It's not even sunrise in Hawaii yet. They can accept it's 11:30 in the morning? Of course not. So especially as train times started becoming more important, being able to say when a train's arriving, when it's leaving, we had to be able to put in a reasonable local time. And that's part of it. So the central part of the United States, where we're at, from roughly Alabama to West Texas on up to North Dakota and Illinois, that is the central time zone. East of there, it's the eastern time zone. West of here, it's the mountain time zone. But mountain time zone only from New Mexico, Colorado, Montana, up to Washington, Oregon, and California. That's the Pacific time zone, 2 hours behind us. You may have heard of Greenwich Mean Time, especially if you're looking at British news sites like BBC.com or something like that. It is, how many hours away are we from English time? That is measured by the Royal Observatory at Greenwich. That is about 6 hours. But during the summertime, just meant for the efficiency of farmers, we have daylight savings time. Most states do. Some are trying to move away from it, but because of daylight savings time, that of course changes where we are in relation. It changes how we measure our time to Greenwich, England, though. The Greenwich Mean Time, also known as Universal Time, on the 24-hour military clock, and it's used especially for astronomers and people working with satellites. So everyone knows exactly what time it is. Regardless of whether you go to daylight savings time or not, you know you're on universal time or Greenwich Mean Time. Astronomers use a Greenwich Mean Time, or universal time as they often call it. So astronomers around the world can look at a similar astronomical event at the same time. But some areas, though, they aren't in a time zone at all. Afghanistan, for example, they never accepted the standard time zone system. This is used all over the world. Russia, the largest country in the world, it spans 12 different time zones. Now, of course, you're going around the world back in all these time zones. Back 1 hour, back 1 hour, back another hour. But what happens when you get to a point that it's yesterday? Well, it came up with something like that. The international date line. The international date line generally follows the 180th meridian for each new day begins. So generally, if you're going east, you lose a day. Yeah, if you're coming east from here, across this line, you lose a day. But going west, you'd add a day. But it's not quite 180 degrees meridian. It kind of zigzags a little bit to avoid splitting up countries or splitting up land masses. So 180th meridian actually is right between Alaska and Russia, and actually intersects several islands and several there, so it kind of zigzags around it to avoid that. We got today, it's Tuesday. Traveling east, it'll become it was Tuesday, but going back east, it'll be Wednesday. Fast forward 12 hours for Australia or wherever. Yeah, it's almost, it's a Wednesday there already. And that's to make sure that everybody's all in alignment. There's this funny story about New Year's Eve 1900. This one ship's captain very cleverly stationed his ship and oriented it on the equator, on the international date line. So at the stroke of midnight, different parts of the ship would be in different hemispheres, different days, and different centuries. So playing with the international date line. So is it time travel? No, it's just a clever trick of the calendar. But going this way it becomes Wednesday, going this way it becomes Tuesday again. Now, global positioning system, GPS. Everyone talks about GPS. It's in your phones. It's how they track uh, your location. Um, it's in your cars. It's in your computers. It's a very handy tool for helping travelers get from point A to point B. Me personally, I prefer old paper maps, but I'm a little old school. Oh well. Well, GPS system, it was conceived in the 1970s and it's maintained by the Department of Defense. And what it is a string of 24 to 28 satellites in geosynchronous orbit around the Earth. The thing about geosynchronous is it's positioned in just a location where it's not affected by the Earth's or the Moon's gravity. Basically, it stays in location. So no matter where you are on Earth, you're always within the line of sight of a GPS satellite. So it's always able to track you. Sometimes there's a little bit of variation because it might reflect off something or whatever, but you're always within the line of sight. And aboard all of these satellites is an atomic clock. So your cell phone is aligned to an atomic clock in orbit. That's why time is exact. It's always the same with everybody's. Even if you may notice you cross time zones, you may notice your cell phone, you don't have to change it manually. The cell phone does it automatically because it's tracking through GPS, those atomic satellites, those atomic clocks. Let's say how accurate atomic clocks are. They lose or gain an average of about 1 second every 30,000 years. They're the most accurate clocks in the world. Why? Because they're based on not they're based on definition of atomic processes, like number of oscillations of an atom of a cesium isotope. I think like 200 million. 200 million equals 1 second, not dividing 1 hour into 60 minutes and dividing a minute into 60 seconds. That's not how they do it. Yeah, the U.S. Naval Observatory, the actual definition of a second is through the definition of an atomic process. Well, by 1972, those are mostly in place, but it's not really until modern computers really get going and with the internet systems that they really become very practical for the general public. A lot of people use GPS systems not thinking about the technology behind it. But yeah, there are at least 4 above the horizon at any time, no matter where you are. GPS receiver records position of satellites simultaneously, then calculates latitude, longitude, altitude, and time. Contrasts exact position and time. Let's show you a couple of things here. Here, okay. This one here is GPS, the Global Positioning System, GPS.gov, keeping score at home. Maintained by the federal government. Next, it has information how to correct address and GPS devices, apps, and online. A lot of people really kind of play with it. But the performance reports of the different satellites and so forth. Checks they go through. Interface specifications, augmentation. We mainly use the GPS system. There are some other countries that have their own system, except like China, European Union, the Galileo system. Russia has its own system. In India. But the global positioning system, that's the gold standard around the world. Of course, different ways to apply GPS: agriculture, soil sampling, data collection, field navigation. Yeah, those tractors you see in the fields, those actually do have GPS in them. Like I say, it minimizes redundant applications, skipped areas, enables maximum ground coverage in the shortest time possible. Basically, how to plow and harvest as quickly as possible and as efficiently as possible. Aviation, of course. Can a pilot fly a plane without a GPS system, without instruments? Yeah, it's called seat of your pants flying. Basically using um, ground features, but it's hard to do, especially when it's cloudy or foggy or if it's night. GPS systems work that out really well. Plus, they have something called an instrument flying, which basically you follow these radio beacons one part of the country to another. But GPS systems help pilots correct any kind of problems of course, reliable and accurate positioning information from planes and so forth. Increases aviation safety. Roads and highways, of course. Millions of people use it all the time. Space features. Of course, how to use GPS? Well, space station does. Shuttle astronauts have used it. So you can help better track where your aircraft, your spacecraft, and where your satellites are. It's by positioning them from one against another. And of course, this does take ground control crews to adjust every so often. And of course, surveying and mapping. Like I say, the GPS system helps give centimeter level surveying results in real time, so you can track down those survey property lines a lot easier. That's just one. What are some of the practical applications of this beyond that for geographers and others? Or something called ArcGIS. This is a big thing in geography now. This is at esri.com. And what you do with this, among other things, is use GPS systems to make maps. Like you see here. Tracking internet outages, tracking weather reports, tracking plane flights. And particularly if you're doing anything like archaeology work, you can pinpoint different sites. Um, you can give information on different sites. You can um, even with businesses and elections information, pinpoint what sites, who's voting, where are the different precinct sites, who's voting in these different areas. Businesses, where are your main zones of distribution, who are your customers. Motion, or they can be static. You can see here. You can build this on a base map or on a computer generated map. All sorts of different ways you can do it. And of course, these satellites, you can, of course, this is Google Earth, of course. See where we are. Now, here's the thing, though, is these aren't quite up to date real time maps. This one was from November 2nd, 2020, but this is I already looked from way up high from space, zeroing in on it, November 2020. And we can zone in a little bit. Here we are right here. Twist around a little bit. The neighborhood. And of course, we can zero in on any area, anything we want. In fact, get close enough, you can actually see cars here. This is the bank on Timber Lane. Samples. There's the post office. Yeah, anywhere on Earth you want to see. Name a site.
Does that have to be in the area?
No, not your ex-girlfriend's house or anything like that. We're not going to go there. Okay.
Can I go to like Alaska or something?
Yeah. Juneau, Alaska. Up and out and in, and here we go. Zero in on it too.
It's still November 2nd of 2020.
Different areas and different sites, but it says that. But yeah, this is Juneau, Alaska. State capital here, this Alaska State Museum. Some call it the Chicken Yard Park. Harbors. Whale Watch Center, which is several blocks from the coast. Their high school. Now, I'd say this is probably summertime in Alaska. Buddhism. Our Review Elementary.
You've seen that people are using, like, they'll buy commercially available satellite footage, everything, so they can see Russian movements in Ukraine and report them to Kiev.
Oh yeah, a lot of people do that. There is some technology you can zero in on this, tell where they're going. There's one system of satellites called Starlink that Ukraine uses to communicate with their troops in the field. Of course, kind of a problem because Elon Musk sometimes gets a little testy and says he's not going to give it to anybody, which means, oh great, they can't fight their battle today. But yeah, some of this is, for example, how they're able to use drones to sink boats in the Black Sea. So using the bouncing off these communication satellites, they can remote control, fly these drones in these different areas and strike targets miles away. And in fact, through ArcGIS, you can map these different locations, figure out their shipping lanes and times, and where's the best opportunity to strike. Any others? Pick spot, any spot.
Why?
Station Pearl Harbor, we can probably see some of the carriers in
Yeah.
the port.
Pearl Harbor. There's a memorial there.
Yep.
But yeah, see the base, Joint Base Pearl Harbor Hickman, field office. See the different dry docks they have here. Docks. Different hangars, the Aviation Museum here. Utah Memorial here. You see, it's a good natural harbor. They're able to kind of, ships are able to work their way in and find their spot here where they need to go. It's the Arizona Memorial right here. As you can see, you got the memorial here. They take boats back and forth. And the Arizona here at the bottom of the sea. I had a friend of mine and also a cousin who was stationed at Pearl Harbor said, yeah, still some oil leaking out of the boat. See the modern Navy, all these big ships right here. It's like a battleship. There's no naval expert.
to convert to museum ship.
Now, a lot of them like that. You go to San Jacinto, Texas, they have the battleship Texas on display there. You can go there, you can tour that big old World War II battleship. Similarly, go to Little Rock in the Arkansas River, the USS Razorback submarine. You can actually take a tour there too. It's amazing how well they can maximize every inch of the submarine for a maximum use. It's impressive. But yeah, with these you can kind of see traffic patterns. You can see, you can map out routes for trips and everything. Like, there's so many different things you can do with it.
So I use my maps app, and I turn on the satellite, and I can look at like Murmansk in Russia, and I can see their aircraft carrier just sitting in dry dock.
Yeah, they've been having real problems even getting the parts together to get it to run, and even getting it out. It's like, so the Russians, they've lost about half their equipment in Ukraine. You know how bad your situation is, and you have to ask Iran and North Korea for military equipment.
Their most modern tank a couple of weeks ago actually got destroyed by a infantry fighting vehicle that is like 20 years old. And it's all service in Desert Storm.
Oh yeah. Said 3/4 of Russian tanks in use in Ukraine today were made before 1980. So in tactical terms, that's called a war of attrition, fighting backwards. So this is just some of the interesting little tools they have. We go from paper maps like this one to use of modern tools of the internet to make all these different devices work. So that's it for today.